Okay. Good evening, everyone. My name is Dr. Ramakrishna Hegde. I'm actually the executive committee member of IEEE Computers Council. I'm a joint secretary of IEEE Computer Society Bangalore chapter. As you're aware that we have today organized one webinar. On behalf of IEEE Computer Society Bangalore chapter, we would like to welcome everyone, with the speaker and everyone. We have Dr. Carlos. Of course, before moving, see, I would like to talk about something about IEEE CS bits APPCAIR. This particular webinar series we have started from the since last year. We have conducted many webinars under this banner, and even this year also, we already conducted one webinar on 18th of May, and the second webinar we are planning to take, and we have one more webinar on June 11th. And of course, we are some more webinars are in pipeline. We are just we are making sure that some knowledge sharing sessions will go on. And today's webinar, as you already mentioned, is on recent research topics in evolution. This actually talk is delivered by scientist, professor, School of Engineering researcher 2013, and also many more award is awarded, and also he published more than 450 technical research articles in various international journals and conferences also. On behalf of IEEE, sir, we'd like to welcome you for today's talk.
Thank you. Thanks for the invitations. Let me share my screen.
Yeah, and also before starting, and
sorry, yeah, you wanted to show something?
No, that's fine. That's fine. That's fine. I think we'll start the session now, straight away. No problem. We'll start. I will hand over the session to you. Sure.
Let's see. Can you see my screen?
Yes, yes, we can see the screen. You can see the screen. Yeah.
Okay. Thanks again for the invitation. The title of this talk is Recent Results and Open Problems in Evolutionary Multi-Objective Optimization. This is an area in which I have been working for more than 25 years. And the outline of the talk is, first, I will provide a very short introduction to multi-objective optimization and multi-objective evolutionary algorithms to motivate some of the research topics that people are exploring today. I will touch on 4 different areas: algorithms, which is the main area in which I work, scalability, parallelism, hyper-heuristics, and then at the end, I will provide some additional ideas, some additional insights regarding research in this area that I believe is worth undertaking in the next few years. Okay, let's start. The notion of multi-objective optimization, in case you are not familiar with it, refers to solving problems having 2 or more objectives that are normally conflicting. That means improving one objective will worsen another one. So what we try to do in this case is to find trade-off solutions that represent the best possible compromise among all the objectives. This means it's not possible to improve one objective without worsening another one. And these solutions are called Pareto optimal solutions. Over the years, and this area started in 1985 with Vega, which is listed there in the non-elitist, non-Pareto-based methods. In the early days, some people found ways of solving these problems without relying on the concept of Pareto optimality. That's why these approaches are called non-Pareto based. There is another mechanism that is very important. It's called elitism. and consists in retaining the best solutions in the population. And this is necessary because of theoretical reasons. And elitism was introduced in the late 90s. So the oldest approaches didn't use elitism, which is the reason why they were called also non-elitist. So these were very simple ideas. For example, linear aggregating functions. The idea is you have a vector optimization problem and you transform it into a scalar optimization problem by simply adding up all the objectives into a single scalar value. You may use weights to generate different solutions, but this sort of approach has the limitation of not being able to generate non-convex portions of the Pareto front. The Pareto front for us represents all the solutions to the problem, all these trade-off solutions, and it's normally a curve. If we have two objectives, it's a line. If we have three or more objectives, it's an n-dimensional. It's always k minus one-dimensional surface, where k is the number of objectives. So if we are with three objectives, it's a two-dimensional surface. And if we have four, it's a three-dimensional, and so forth. So in the old days, we had very simple approaches that consisted in transforming the problem, the original problem, into something easier to solve. And people use, of course, different types of evolutionary algorithms, mostly genetic algorithms. And the first actual algorithm that was explicitly designed for dealing with a multi-objective problem was the vector-evaluated genetic algorithm introduced by David Schaefer. He was proposing his PhD thesis in 1984 and was published at two conferences in 1985. This was a very simple algorithm in which he divided the population into as many subpopulations as objectives he had. And in each subpopulation, he selected based only on one objective. So he normally solved problems only with two objectives. So subpopulation 1, he selected based on objective 1. Subpopulation 2, he selected based on objective 2. And then for crossover, he forced the recombination of the best solutions in objective 1 with the best solutions in objective 2. The aim was, since crossover is some sort of interpolation, he wanted to get the best possible trade-off between the objectives. In practice, what he was doing, since he was using proportional selection, is equivalent to a linear aggregating function. It was not really that innovative, but at that time it worked for the problems he wanted to solve. It was a simple problem in machine learning with two objectives. And there were others, I won't get into details, like the epsilon constraint is a transformation method, and target vector approaches. These are non-linear aggregating functions, which, unlike linear aggregating functions, they do have the advantage that under certain conditions, they can generate non-convex portions of the Pareto front. Then in the 90s, starting in the mid-90s, some researchers started to propose multi-objective evolutionary algorithms that incorporated the notion of Pareto optimality. However, these algorithms were still very simple, very naive, more sophisticated than the ones proposed in the 80s, but still didn't have, for example, elitism. So from here, perhaps the most remarkable case is MOEAS, the multi-objective genetic algorithm proposed by Carlos Fonseca and Peter Fleming, when Carlos was a PhD student at the University of Sheffield in the UK. And this was a very interesting algorithm. It was based on an idea proposed by David Goldberg in his famous book on genetic algorithms, since it used something that we call today Pareto ranking, or today is known as non-dominated sorting. It's a ranking procedure to assign a value to solutions that doesn't correspond necessarily to a fitness value, but more to a ranking based on Pareto dominance, on Pareto optimality. So solutions which are Pareto optimal, and normally there is more than one, they get the same fitness value, so that during the selection stage, they are all selected with the same probability. And solutions that are dominated, that means these are not good solutions, they get a lower fitness value, which is proportional to how many solutions dominate. So MOEAS and NSGA, the non-dominated sorting genetic algorithm proposed by Kalyan Moideb, in 94. These were very early algorithms that were adopted by several people at that time during the 90s. And there were other interesting ideas like the niche Pareto genetic algorithm, MPGA, proposed by Jeffrey Horn in 1994, which can be seen as a variation of MOGA with a clever selection procedure that reduced the computational cost, because instead of comparing every solution against everybody else, in MPGA, he only took a sample from the population, a sample of solutions, relatively small sample of 10% of the population size, and he estimated the rank of the solution using this sample. And he was able to show empirically that this was good enough to produce reasonably good results. So these algorithms became popular to a certain extent during the 90s. However, their designs still had a lot of room for improvement. For example, NSGA was not particularly efficient. MOGA was the best in this generation. MPGA was faster than MOGA, but not as good as MOGA in terms of the solutions that it generated. And then we have what I call the contemporary approach. The contemporary approaches are those that are Pareto-based, but are also elitist. Elitism was introduced formally into SPA, the Strength Pareto Evolutionary Algorithm, developed by Eckhard Sitzler and his advisor Lothar Thiele at ETH Zurich. This is a very interesting algorithm. Basically, what he does is to retain all solutions that are Pareto optimal, or we call them also non-dominant solutions, and he used these solutions to decide which individuals to select. So the selection mechanism not only considers solutions in the main population, but also solutions in what he called the external population, which was a data structure in which he stored the Pareto optimal solutions that had been found so far. However, Sitzler realized that by doing that, there was a problem. Normally, the number of non-dominant solutions started to grow very quickly, and this diluted the selection pressure, and he realized that he could not allow the number of solutions to grow out of control. So he introduced a mechanism based on a clustering technique to prune the contents of the external archive periodically. He set a bound, a maximum value on the number of solutions that the external archive could contain. And once he reached this value, then he will activate the clustering algorithm to prune solutions. So this was a very elegant way of maintaining diversity, and it was also very effective. So this algorithm became very popular. There was SPA2, but SPA2 was really a small variation of SPA. The main algorithmic design was exactly the same. And then, of course, we had NSGA2. NSGA2 is very different from the original NSGA, except for the name. It was also introduced by Kalya Moideev, who at that time was at IIT Kanpur. And this is a very interesting algorithm. The main component of the algorithm has to do with an operator called the crowded comparison operator, in which he finds a way of discriminated solutions based on diversity without requiring an additional parameter, because most algorithms were using, for example, fitness sharing, but fitness sharing requires a parameter. And this approach didn't require any. The problem was that the crowded comparison operator is not really scalable. It was not meant to be used with more than 3 objectives, because it degrades very quickly, because it's based on geometrical properties of solutions in the Pareto front. And there were many others, like the Pareto archive, the microgenetic algorithm that we introduced in 2001, and many, many other algorithms, most of which are already forgotten. And then we have what we call the recent approaches, although they are not really that recent, like MOEAD, the multi-objective evolutionary algorithm based on decomposition. It was introduced in 2007, but still is in use today. Many people have proposed variants of this algorithm. And the idea is quite interesting, because MOEAD, what it does is to transform a multi-objective optimization problem into several single-objective optimization problems, in which the search is conducted simultaneously for all these problems, and they use neighborhood search to find all the solutions very efficiently. This algorithm requires something that we call a scalarizing function, because the scalarizing function is the one responsible of the transformation, and it also uses weights. However, the algorithm is scalable, so it can be used with any number of objectives. Nevertheless, as we increase the number of objectives, the number of weights will also increase, but the increase is linear, so it's not that bad. Then we have the indicator-based approaches. This is an intriguing idea. I will explain this in another slide. We have the indicator-based evolutionary algorithm, SMS-MOA, which is a variation of NSGA2, Hyper and others. And then we have NSGA3, which is really a variation of a decomposition method in which they rely on reference vectors rather than using a scalarizing function, but the idea is very similar. So it's an extension of NSGA2, which is meant to be used in what we call many objective optimization, which refers to multi-objective optimization problems having more than 3 objectives. This is just to give you an idea. It's not up to date because of the pandemics. I have had problems to contact my assistant to update the repository. But you can see the growth, at least until 2019, the growth in the number of publications on EMO starting in '84 with the PhD thesis of David Schaefer. You can see that during the 90s, there was a very modest number of publications available. However, at some point, you can see peaks like in 2009 with over 1,000 publications per year. So at some point, EMO, Evolutionary Multi-Objective Optimization, became a very, very popular topic. So the obvious question is, after all these years of existence, which actually is more than 33, will be 35, this area seems intimidating to people. If a PhD student wants to work in this area, they feel frightened because they say, what can I do? There are so many papers available. So what remains to be done? And this talk is about that. So let's start with algorithms. As I say, I'm going to touch on 4 topics. Let's start with algorithms, which is my main area. So again, I'm going to revisit the 3 different families of multi-objective evolutionary algorithms to show you the limitations that each of these families has. So let's start with Pareto-based. This is the old approach, the traditional one. In Pareto-based multi-objective evolutionary algorithms, this selection mechanism is based on Pareto optimality, as I already mentioned. Most of these algorithms adopt non-dominated sorting or Pareto ranking, which is basically a mechanism to assign fitness based on Pareto optimality. It's not based on objective function values directly as it's done in single objective optimization. Now, all these algorithms adopt something we call a density estimator. The density estimator is a mechanism responsible for keeping a variety of solutions in the population. This is very important because we don't want the algorithm to converge to a single solution. And because of stochastic noise, normally evolutionary algorithms, if you run them long enough, they will converge to a single solution. So there have been several mechanisms proposed over the years for the density estimator, going from crowding, fitness sharing, entropy, adapted grids, more recently parallel coordinates, and so on. The main limitation of these approaches is scalability in objective function space. As we increase the number of objectives, this sort of approach gets in trouble. Why? Because if we have more objectives and we don't increase in a non-linear way the population size, then very quickly all the solutions will be non-dominated or Pareto optimal. And this is bad because that means all of them are equally good. So we won't have any information to guide the search. And if this is the case, we are basically selecting at random. And this is very bad. There is a way around, a relatively easy way, which is to modify the density estimator. And some people have done this, but for some reason, it's not a very popular approach. Second family, the composition-based. These are approaches like MOEAD that I already mentioned. The idea is to transform a multi-objective optimization problem into several single objective optimization problems, which are solved simultaneously using information from the neighboring subproblems. These approaches, the main limitation has to do with their dependence on a scalarizing function. It has been found recently that these approaches are very sensitive to the geometrical shape of the Pareto front. If the geometrical shape of the Pareto front doesn't fit a simplex, then they don't work. They need to be modified. There is some research going on right now in that direction. So in this case, they are scalable. I already mentioned this before, in the sense that if you increase the number of objectives, you need to increase the number of weights, but the algorithm still works. And the increase is linear. So it's affordable. It's okay. You will have a larger population size, perhaps 300, 500 individuals, but it's not a big deal. It's not going to be 10,000 solutions. And the last family is one family I particularly like, is indicator-based multi-objective evolutionary algorithms. In this case, the original idea was to adopt a performance indicator for the selection mechanism instead of using Pareto optimality. However, over the years, people realized that it was not really necessary to use the performance indicator in the main selection mechanism, that they could simply use it in the density estimator. And that's the idea, for example, of SMSI-MOA. SMSI-MOA is the NSGA2, but they replace the crowded comparison operator, which is not scalable, by the hypervolume. The hypervolume is a very intriguing performance indicator that if you always maximize the hypervolume of a set of solutions, you are guaranteed to converge to the true Pareto optimal set. However, the problem is that the hypervolume is the only performance indicator which is known to be Pareto compliant. This means it's compatible with Pareto optimality, but it's very computationally expensive in high dimensionality. The cost of the hypervolume grows polynomially with the number of solutions, but exponentially with the number of objectives. So it becomes unaffordable very quickly. After 6, 7 objectives, it's just too expensive to compute. It may take hours or even days to perform a single execution. There are other performance indicators which are not Pareto compliant. They are weakly Pareto compliant. But in practice, they work reasonably well. However, most researchers don't like to use them. We have, for example, R2, IGD+, and a few others. Okay, so now a common practice in today's research, particularly in top journals, I'm currently the editor-in-chief of the Transactions on Evolution Computation, is that people propose what they call a new or a novel algorithmic variant of an existing approach, and they test it in a very comprehensive way with many test problems, many performance indicators, and they compare against many algorithms. But, and this is okay, it's sort of research by analogy. However, the question I always raise is, are we heading somewhere with this? When the variant is well justified, for example, is for dynamic multi-objective, okay, that's okay, because we do have dynamic multi-objective optimization problems, and we need tools to deal with these problems. But in many cases, it's not really that clear what will be the usefulness of this variant. But the question is not that. The question for me is, can we design multi-objective evolutionary algorithms based on a different idea rather than just proposing variants? Somebody needs to propose new algorithms, as we had in SGA3 or MOEAD. So the question is, do we still have room for these new algorithms? And I believe the answer is yes, of course. Some years ago, as a simple example, I had this master's student who came up with a very interesting idea. He proposed a methodology by which an arbitrary nonlinear multi-objective optimization problem is transformed into a linear assignment problem. And if you are familiar with the linear assignment problem, there are algorithms to solve it that have a polynomial complexity. For example, the Kuhn-Munkres, also known as the Hungarian algorithm, is order n to the third, but still polynomial. So you can use this algorithm to solve in a deterministic way the resulting problem. The approach proposed by this guy, by Molinet, still requires something similar to a density estimator, but it's a very simple approach. And the intriguing thing is it doesn't seem to belong to any of the three families of algorithms that I previously indicated. It's not Pareto-based, it's not indicator-based, it's not decomposition-based. It has some features similar to indicator-based, but it's not exactly indicator-based. Other ideas are, for example, to try to understand the limitations of the algorithms that are currently available. For example, some years ago, we tried to study the properties of different scalarizing functions because they are used both in the composition-based methods and in some indicator-based methods. So we wanted to understand if there were scalarizing functions that provided advantages over others. This was something in which I was very interested, and we found that it is true that some of them offer more advantages. Other interesting ideas is, for example, the idea of amalgam, which is an algorithm that combines different multi-objective evolutionary algorithms under a single control mechanism. It's also another intriguing idea, which is similar in a way to hyper-heuristics, something I will mention at the very end. Another idea is to combine components of a multi-objective evolutionary algorithm under a framework that allows to exploit their advantages. And in this direction, a very interesting proposal is BORC, this approach developed by Hatka and Patrick Reed in the US, which incorporates, among other things, epsilon dominance, a measure of convergence speed, which they call epsilon progress, an adaptive population size, that means the population size can change over time, multiple recombination operators, and a steady state selection in which only one solution is replaced at each iteration. And some people have thought of this sort of approach as the first step towards the automated design of algorithms, which is a dream in the field. There are people currently working on automated parameter tuning, but what about designing automatically an algorithm in which you have all the components and then you input is the problem and you try to find combinations of these components that are the best for this particular problem. Of course, you need a lot of computer power to this, but some people see this as the future of the design of multi-objective evolutionary algorithms. Okay, let's move to the second topic. Second topic is scalability. As I mentioned before, in objective function space, if we go beyond three objectives, these problems are called many objective optimization problems. And the main limitation of Pareto-based multi-objective evolutionary algorithms has to do with this problem I mentioned before, that we have an exponential growth in the number of non-dominated solutions as we increase the number of objectives. And this makes these selection mechanisms completely useless because all the non-dominated solutions are considered equally good. In the early days of this field, back in 2006, 2007, there were two main approaches to deal with many objectivity. The first was to use a relaxed form of Pareto dominance. It is possible to relax the original definition of Pareto optimality so that it's not completely orthogonal, that there is flexibility to select solutions. And this is sort of the most elegant and mathematically correct approach to deal with many objectivity. The second approach that people used for a few years was dimensionality reduction, to reduce the number of objectives during the search process or after the search. The idea here is that if we have, for example, 7 objectives, it's very unlikely that all these objectives are going to be in conflict with each other. So we can analyze the level of conflict and try to remove some objectives that are non-conflicting. So we focus initially the optimization on the conflicting objectives, and later on we incorporate the non-conflicting ones. So for example, Dimo Brokov was working on that back in the year 2006, 2007, and proposed an interesting algorithm for doing this both in a deterministic and in a stochastic way. And there are, of course, many other ideas, including, for example, the use of machine learning, or what we call EDAs, estimation of distribution algorithms, the use of performance indicators, epsilon dominance, which is another relaxed form of Pareto dominance, but this is used for archiving, not for selection, or the two-archive multi-objective evolutionary algorithm, which is an interesting approach that uses one archive for convergence and another one for diversity. As I mentioned before, scalability is an issue because there is empirical evidence that indicates that once we reach 10 objectives, even random search is more effective than a good algorithm like NSGA2. But there is another interesting problem related to scalability. As we increase the number of objectives, the number of solutions required to sample the Pareto front also grows exponentially. That means you will need a very high population size to sample all the search space. And this is normally an issue because this is unaffordable. However, when I got into scalability some years ago, for me, I was not so interested in developing algorithms. For me, the real question was, what is the source of difficulty in many objectivity? In other words, I was skeptical about scalability being the only source of diversity. I wanted to find out if there was another one. Ichibuchi has an interesting paper from 2015 in which he considered 5 types or sources of difficulties in many objective problems, including very obvious ones like difficulties to generate a good approximation of the whole front because you are sampling a very high dimensional space with few solutions, and others that are not so obvious, like how to assess performance. For example, how to assess distribution of solutions in a very high dimensional space. This is not trivial to do, not with the indicators we have. But back in 2011, we had already stepped into a very intriguing and shocking result related to scalability. After doing some study, which came out by accident, we concluded that adding more objectives, that means scalability per se, is not necessarily a source of difficulty in multi-objective evolutionary algorithms. We were able to show that there are problems in which you can increase the number of objectives, and this doesn't make the problem more difficult. And others in which having few objectives, the problem is arbitrarily difficult for a multi-objective evolutionary algorithm. Why? What we found was that the real source of difficulty was related to what we call the descent cones. These are the search directions generated by the gradients of the objectives. I won't get into details because I won't have time, but it's a very interesting result. And Ichibuchi found a similar result regarding correlation. He found out that if you have a high number of objectives, but the objectives are highly correlated, algorithms like NSGA2, which is not designed for many objective optimization, can provide very good results. So that means scalability per se, again, is not necessarily a condition to make a problem more difficult. There are, of course, many other topics related to scalability that are worth exploring in the future. For example, density estimators. What sort of density estimators can we use if we have, for example, 10 objectives? Visualization, how can we display a Pareto front of 10 objectives? It's very challenging because the human eye is not used to seeing this, to getting information from such a high dimensionality. Also, how to design performance indicators suitable for assessing performance. For example, for convergence, we can use hypervolume, but it's very expensive. So the question is, what else can we use? What other performance indicators can we use? And what about the scalability in decision variable space? This is another interesting topic. What happens if perhaps the problem has only 2 or 3 objectives, but a very high number of decision variables, let's say 10,000 decision variables? Back in the year 2007, Xinfu Zhang, the guy who created MOEAS, had already analyzed how scalable his algorithm was. and they tried up to 100 decision variables, and the algorithm was still working properly. However, we conducted another study in 2008, and we found out that the algorithms that were in use at that time, getting to at around 256 decision variables, they started to produce very poor results. And once we reached 500 decision variables, the maximum was 1,024, but after 500, everybody did very badly, very poorly. Results were very bad. So that meant that these algorithms were not designed to solve problems of high dimensionality in decision variable space. In 2013, with a former student of mine, we proposed the first multi-objective evolutionary algorithm that was explicitly designed for large-scale multi-objective optimization. That means multi-objective optimization problems with more than 100 decision variables. This algorithm is based on cooperative coevolution, which is the that people use in single objective large-scale optimization. And we were able to solve problems having up to 5,000 decision variables. Now, of course, there are other interesting ideas here related to this. Why don't we design a benchmark for problems with a high number of decision variables? There are some benchmarks that can be used. Some of them are not very appropriate, like the DTL set, because they get increasingly complex with the number of decision variables, but some people have used them. The set DT have been used as well, but it would be nice to have a particular benchmark for large scale, a different one from the ones we normally use. And what about large scale many objective? What if we have many decision variables and many objectives? There are already people working in that direction, but this is another interesting idea. We move to the third topic, to parallelism. It's very obvious why do we need parallel multi-objective evolutionary algorithms, because we do have in the real world many problems having very highly expensive or computationally expensive objective functions that we need to evaluate. However, something interesting and a bit surprising is that the design of new parallel multi-objective evolutionary algorithms is very rare, even today, in the specialized literature. There isn't much work on this. We are lacking, for example, work on the development of asynchronous parallel multi-objective evolutionary algorithms. And asynchronous architectures are very common today. Most people have clusters of computers which are not homogeneous. The processors are different, and they are some processors are faster than others, so we need to balance the load to make the best possible use of these computational resources. We also need more work on the design of parallel multi-objective evolutionary algorithms designed to run on graphical processing units, on GPUs. There has been already some work in this direction, but more needs to be done. Other ideas, for example, some years ago, we came up with this interesting idea that actually the original idea was not ours. It was proposed by Eric Goodman before in 1996. We decided to design a parallel multi-objective evolutionary algorithm with a change of granularity. This was a migration in a single direction. It was a unidirectional migration. But in the first island, we had a very coarse granularity. So for example, let's say the decision variables were real numbers with 8 digits of precision. In the first cluster, in the first island, we use integers rather than real numbers. Once the population started to converge, we migrated to the following island using real numbers with 1 digit of numerical precision. And we kept migrating so that in the last island, we use the full precision, real numbers with 8 digits of precision. What we found out with this sort of design was that this was way more effective than using the entire precision in all the islands, because the change of granularity allowed a smooth change during the search and allowed a better exploration of the search space. So it was a very interesting result. It was based on something called the injection island genetic algorithm that was proposed in the 90s for single objective. This is the multi-objective version. Other ideas, for example, to combine asynchronous parallelism with the use of micropopulations. This is something we did with a former PhD student of mine in an algorithm called the APPCAIR, which is the parallel micro optimizer based on the S metric. The S metric is another name for the hypervolume. This was a very interesting approach because this is a multi-objective evolutionary algorithm based on the hypervolume whose computational cost is affordable because the population sizes in each island are very small. And we were able to show that this provided a very good performance in spite of the fact that the population sizes were very small. So it was very, very intriguing, and unfortunately, not many people follow up on this work. Another idea is, of course, to exploit the parallel architectures that we have available for a particular multi-objective evolutionary algorithm, rather than producing some sort of a straightforward parallel implementation of a well-known algorithm such as NSGA2, NSGA3, MOEAD, SMS, MOA. We want to be creative in this regard. But of course, if you want to do research in this area, this is very fertile area because not much research has been done on parallelism. So we need, for example, to study fitness landscapes of parallel multi-objective evolutionary algorithms, the impact of the topology in the performance of a parallel algorithm, automated parameter tuning, decomposition-based parallel multi-objective evolutionary algorithms, indicator-based, diversity management, and so on. There are many, many topics that are still worth exploring in this area. Let's move to the last topic, which is hyper-heuristics. Hyper-heuristics are a very interesting idea. The idea here is to combine several types of heuristics which are somehow complementary with the aim of providing a more general optimizer. That means an optimizer that can be applied in a wider class of problems. The main motivation of hyperheuristics is to have this more general view without having to rely on the use of separate optimizers. You put them all together. This is really the idea. Originally, hyperheuristics were proposed for discrete search problems, in particular domains such as scheduling. They were very popular. But it is also possible to use them in multi-objective optimization and not only in discrete search spaces, as we will see in some of the references I will show you. So, for example, Edmund Burke, which is a guy who has worked a lot on hyperheuristics, he developed some multi-objective hyperheuristics like this one from 2005, in which he extended the reinforcement learning with taboo search heuristic selection method that he proposed in 2003, using a fixed size taboo list for multi-objective optimization. And this was used for space allocation and timetabling. Timetabling is another form of allocation, which consists in allocating rooms for students. This is one of the few multi-objective hyperheuristics that has been designed for continuous optimization, proposed by McClellan and Kidwell in 2011. It's a very interesting approach, MCHH. And it applies a heuristic selection method modeled as a Markov chain to the well-known DTL set test problems that are very popular in multi-objective optimization. Maashi in 2014 proposed an online learning selection choice function based hyperheuristic framework for multi-objective optimization, in which she combines the strengths of three very well-known multi-objective evolutionary algorithms, NSGA2, SPA2, and MOGA, not sort of the most recent ones, but they are very popular. And these three algorithms are used as the low-level heuristics. That means she makes combinations of them in her search. Another interesting proposal by Walker and Kidwell in 2016, they proposed the MOSSHH algorithm, which is an indicator-based, multi-objective, sequence-based hyperheuristic. This is the first attempt to use a hyperheuristic in many objective optimization problems with more than 3 objectives. And it's a very interesting study in which they compare 3 indicators. One is based on average rank, which is an all selection approach. Another one is based on the hypervolume, and one more on the favor relation, which is also an all approach, but is not completely compatible with Pareto optimality, but was used back in the early 2000s. And this is combined with Pareto dominance for solving many objective problems. It's a very interesting idea. Gonsalves in 2015 proposed a multi-objective hyperheuristic based on a choice function to adaptively select appropriate low-level heuristics, that means operators, for MOEAD. And the low-level heuristics in this case consisted of 5 differential evolution operators. More recently, with a former PhD student of mine, we proposed in 2017 a hyperheuristics, which is quite different because it combines scalarizing functions. It's not operators, it's not algorithms. It's scalarizing functions which are used for an indicator-based multi-objective evolutionary algorithm, which is based on R2. R2 is a very intriguing performance indicator. And this selection is conducted through another indicator, which is called S-energy, which measures the even distribution of a set of points in k-dimensional manifold. So it's very interesting work. What else can we do? Of course, we need theoretical studies on the use of hyperheuristics in multi-objective optimization. And there is already some work in that direction, like this paper by Qian from 2016. He provided a theoretical study on the effectiveness of selection hyperheuristics for multi-objective optimization. And they concluded that applying selection hyperheuristics to any of the 3 major components of a multi-objective evolutionary algorithm, which could be selection, mutation, and acceptance, can exponentially speed up the optimization process. Another interesting idea is to combine performance indicators. And this is something that Guillermo Falcón did with me. He was my PhD student, recently graduated last December. And he, in this work from 2018, he combines several density estimators. It's also another interesting idea. So to finalize my talk, the main challenge, of course, in the next few years is to continue to open new venues of research in NEMO. This is becoming, of course, increasingly difficult because there are less venues that remain to be open, and there is a huge volume of research in the area. So we need to be more creative. As Albert Einstein used to say, imagination is more important than knowledge, but I will have to add that in this field, imagination requires knowledge, so cannot go by itself. So personally, I believe that there is still plenty of topics that are worth exploring in NEMO, but some of them require us to move outside the mainstream of the research that is currently being conducted. So for example, we need new performance indicators, particularly for many objective optimization, because we don't have, for example, good indicators for assessing diversity in high dimensional spaces. There are, of course, some interesting choices that people are using recently, like the S-energy that I mentioned before, but we need more. We need to explore more what has been proposed in other areas. Another important topic is to design new mechanisms, for example, new encodings, new operators, and so on, for multi-objective evolutionary algorithms based on specific features of real-world problems. For example, variable length encodings, expensive objective functions, problems that have uncertainty, and so on. This is an example for variable length problems. Also, there are other ideas around there that have not been properly exploited in multi-objective optimization. One of them is coevolution. Coevolution is a very intriguing concept that was very popular back in the year 2005 in evolutionary computation, but hasn't been used much in multi-objective optimization. So besides large scale problems, which is a potential application of cooperative coevolution, coevolution can be used also in dynamic multi-objective optimization and in other areas. Actually, is related to game theory as well. So to finish with this discussion of challenges, it's important to keep in mind that a great source of diversity regarding research idea is the knowledge coming from other disciplines. So even if you are not from NEMO, that's not necessarily bad. Actually, can be very good because you may have a different view of the field than those who have been only working on NEMO for many years, like in my case. So for example, our field has adopted data structures that are very advanced and proposed in other areas. We have used, for example, red-black trees. We have also adopted concepts from computational geometry, like the Voronoi maps, convex hulls, and quad trees. And we have even adopted concepts from economics, like game theory. All of this has been used to design novel multi-objective evolutionary algorithms and novel operators. We also need to explore more ways of bridging the gap between operations research and EMO. An example is the design of hybrid approaches, algorithms in which you combine a multi-objective evolutionary algorithm with, for example, a gradient-based method. This is something we did some years ago. And there is also some interesting work from Kalyan Moedeb, in which he uses the Karush-Kontoker optimality conditions to estimate proximity of a solution to the Pareto optimal set. That means to define a stopping criteria for a multi-objective evolutionary algorithm. So, and summarizing, I'm convinced that EMO is still a very promising research area which should remain active for many more years or so, I hope. But we need to increase diversity in our research topics, and we need to be more disruptive. This is particularly important for young people. We only do work by analogy, of course, we will suffer stagnation. If you want to know more about EMO, you are welcome to visit the EMO repository, which currently has over 12,600 bibliographic references, which includes more than 300 PhD theses, lots of papers, contact info of several EMO researchers, and very important, several public domain implementations of well-known algorithms. We have links, for example, to libraries like PlatEMO. PlatEMO is implemented in MATLAB and contains the implementation of 100 multi-objective evolutionary algorithms. And this is all from my side, and I'm open to any questions you may have. Thank you.
Yeah, thank you very much, Dr. Carlos. I think a great session we witnessed, and we actually opened the research area for us, and most of us, we are passionate researchers. I think given one of the very interesting area where we can involve, and very challenging also. Yeah, thank you very much for that. And I request any participants have any questions, you can put in the chat box, please. Any queries, if you have, please, you can put in the chat box. Anybody having any questions, please? Anyone having any questions, you can put in the chat box, please. Maybe you can post it later also. That's fine. And for information to the participants, I have just put on the feedback link already. Please kindly fill up. And do anybody having any queries, please? Anybody having any questions, please? I think if no one is having any questions, I think we'll move on to the. Thank you very much, Dr. Carlos, on behalf of IEEE Computer Society Bangalore chapter, and on behalf of all the participants, we would like to thank you, extend our sincere thanks to you for delivering such a wonderful knowledge sharing session to us. And you eye-opened us some of the research area, some of the challenging area where we can involve. We personally, being a researchers, we are, we created, you created some interest in those areas, and who identified some area where we can able to work on. Thank you very much for that. Thank you very much.
Thank you.
Thank you. Thank you. And on behalf of IEEE Computer Society, we'd like to honor with a beautiful tree for you. This is one of the initiatives. And this
Looks
is
nice.
to save the tigers, and honor with your beautiful tree for you. So this certificate we are going to mail you by tomorrow.
Okay.
Yeah. Thank you very much.
Thank you.
Once again, yeah. Thank you, Dr. Carlos. And I would like to thank all the office bearers of IEEE Computer Society and all the participants gathered today. Thank you once again. Dr. Vishwas, are you there? Vishwas, are you there? It's fine. Yeah, that's okay. So, yeah. We conclude the session, Dr. Carlos. Yeah.
Thank you.
Thank you very much.
It was
Yeah,
a
thank
pleasure.
you very much. Yeah, thank you. Thank you very much. I'm sure we definitely will call you for the more sessions in future also, because one of the very interesting area you opened for us. We'll work on that. Thank you very much. Yeah, thank you.
Bye-bye.
So yeah, bye-bye. Thank you very much. Thank you. Thank you all the participants. Please fill up the feedback link. Okay. Yeah, thank you.